Right. So yes, hardware acceleration case study, neural network accelerators. So at this point, there's really no need for us to talk about the usefulness of deep neural networks or further emphasize the obvious, because everyone pretty much agrees it's one of the big pieces in modern society. It's really, really useful. It works really, really well. It's used for many, many applications, including image and video recognition. My avatar that is on the screen right now actually uses a neural network for what is called facial landmark detection. So this neural network looks at the video stream of my actual face and then recognizes where various points on my face are located on the screen, where my different positions of my mouth are, whether my eyes are open or closed, where my eyebrows are, which direction is my face facing. Things like that are determined by the neural network. Self-driving cars use a lot of image detection, object detection from video streams to determine where the other cars are. And it would be, there's no point trying to point out every single application in which neural networks are useful for. So I won't. This is just a very small example of the things that people are working on. And one of the earlier applications, and because they're kind of relatively simpler, this is the one that we're going to focus on for the remainder of this sub-lecture, is the topic of image recognition, where if you give a single photo with ostensibly one object in it, it could have some surrounding, it could have some occlusion, whatever, but if it has one large image object in it, it is up to the neural network's job to classify which object this photo is about. Is it a photo of a person? Is it a photo of a flower? Is it a photo of a dog or a cat? So on and so on. So image recognition. And this was one of the very early important applications early on in the area of machine learning and neural networks. And one of the key benchmarks for the accuracy in neural networks is ImageNet, Image at Large Scale Visual Recognition Challenge, or ILS-VRC. And this is where the new neural networks that are trained by everyone, research labs and industry, Microsoft, Google, all those people come to compete on a fixed set of images to try to test each other, whether to see how accurate each of them can be. And as time moves forward, so this is classification error for, I think, the top five classification accuracy. So if for every single photo, the neural network gives a top 5 list of what it thinks it is, and it checks if the correct answer is among it, because there may be more than one object in the photo, for example. And accuracy has continuously increased, so lower is better in this example because y-axis is classification error. So accuracy became better and better over the years, slowly. But in 2012, AlexNet, the model I was talking about before the lecture, came out, which was, there are many asterisks here because a lot of these points are contended, but it was the very first fast GPU accelerated deconvolutional neural network to win a image recognition contest. So there's a lot of prefixes, there's a lot of conditionals here, but the impact of this model was fairly large. So the accuracy suddenly became very, there was a pretty big jump in accuracy, and every single model that won the challenge since has been neural network based. And because suddenly, overnight, it seemed, the neural network model for the machine learning model, this piece of software, was doing human level accuracy, getting human level accuracy in image recognition tasks. This became of very big interest to everyone. And I think around 2014 and 15, with accuracy in these levels, the best neural networks started becoming better than human beings on average on image recognition tasks. So this became a very machines became very good at recognizing images. And this technology is being used not just for this kind of approaches, general purpose approaches. It's being used to recognize cancer cells in bloodstreams and whatnot. There's a very wide range of applications, even for this single application. And some of you may be familiar with all of this already, but just for the purpose of setting the field, so to speak. So here's an overview of deep convolutional neural networks, the architecture. And this is not to say that this is how all neural networks work. There's various different classes of so-called neural networks that may have different overall architectures. For example, recurrent neural networks, LSTMs, autoencoders, all this stuff, they all have different, slightly different looking attention-based networks. They all have different looking architectures. But since deep convolutional neural networks are kind of one of the first and it's easiest to understand, we're going to focus on that. Yes. Typical deep convolutional neural networks consist of two different, and even that is kind of disingenuous, largely two different classes of layers. And the whole model is organized as a stack of these layers. Typically, earlier layers are convolution layers. We're going to talk about what that is in a bit. Later layers are so-called fully connected layers. Different models have different combinations of how many of these things there are and what the configuration of each of these layers are. And you feed an image or a video frame into the first convolution layer. This does some filtering work. It feeds into the next layer, 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 feeds into the next layer. And at the end of the fully connected layer, it emits a vector of all possible potential classes of images. So if this model has been trained to recognize 1,000 different types of objects, it will emit 1,000 floating point values at the end of classification. And we can know what object this neural network thinks the photo is based on the so-called softmax filter, looking at all the floating point values and picking the largest one. So for example, in this example output, the neural network thinks this photo has a 0.002% chance of being a goldfish, but 89% chance of being a palace. So once we scan through this entire list, palace might be array index 24, for example. So if array index 24 has a value of 89%, and we know that array index 24 represents a palace when we train the model, we can know that the neural network thinks that the input photo is a palace. So that's good. This is fairly simple enough. And using this model consists of two different phases, training and inference. So the neural network model that we showed, that we saw in the previous slide, represents billions and billions of weights that need to be trained. And we'll get into what those weights are and how they interact with each other in a bit. But the value that each of these weights have, and in the context of lab 1, the weights will be the values inside the matrix, the weight matrix and the bias array. The value that each of these positions have, they need to have the correct values to actually function correctly. So training is the phase in which we take a lot of training data, hopefully labeled training data. Of course, there are different ways of dealing with unlabeled. This is a very wide field, but we're going to restrict ourselves to when we have labeled training data. This is a photo of a palace. This is a photo of goldfish, etc. We have 10 million of these kind of photos. And we can train the model by tuning the parameters using these training data. And the key component of this is the backpropagation algorithm, which uses, and it's not important to get into what all these means right now, but backpropagation using stochastic descent is the most popular algorithm, and it has a pretty high time complexity, requiring a lot of computation throughput. But since training, unless, again, there's a lot of caveats, there are incremental training that you can do in the field on your phones, but if we don't think about that for a moment, typically training, at least initially, is done in data centers and doing in data centers using lots of computation, lots of power that's available there. And because training algorithms do change rapidly, at least a few years ago, they were changing very rapidly. The most popular hardware for training is a cluster of machines using GPUs. So here, I mentioned that there's a low demand for application-specific accelerators because if we're just working in a data center where we have pretty much near unlimited amount of power, and we can take advantage of the economy of scale. We have a lot of space, cooling, things like that. It's simple to just install a machine with a bunch of off-the-shelf available GPUs and write software for it. I said this, but this is not technically always true because the Google TPU exists, which is an application-specific accelerator for training as well. And their paper actually states that the biggest goal for TPU version 3 was improving its training accuracy, training performance. So this phrase is not necessarily entirely true, but relatively. The other phase in using neural networks is inference. So we have a trained model and we apply it to the actual application. So if we talk about image classification, this model can be used to determine the class of a new input data, a new video frame or a new photo. So we use a trained model and we can determine the class of a new input data. And inference, of course, this inference can also occur in the data center as well. If Google is using it for their search indexing, et cetera, that happens in the data center. But it can also happen, compared to training, this happens more often close to the clients, close to the actual use case. For example, if you have a Google Home device at home and you say, okay, Google to it, there is a neural network on the device itself. Without having to send all the audio data to a server, there's a neural network installed on the device itself to recognize that one phrase. Similar things happen on your phone, so on and so on. So if inference can occur closer to clients, meaning the low latency and power efficiency constraints is a little bit more stringent compared to when you're doing training. This is why for inference, there's a larger demand for application-specific accelerators, ASICs, for doing neural network inference. And you may ask, since if we have a lot of, if you are sending all raw data to the server to do all neural network inference on the server, that of course puts a lot of pressure on bandwidth. It has privacy concerns. It also puts a lot of pressure on the data center bandwidth, so on and so on. So if data computation can be offloaded to the so-called edge, it is very, very beneficial. Right. So components. So we mentioned that there are two different components, different types of layers in the neural network, fully connected and convolutions. We'll first look at the convolution part. The piece of code that you worked with for lab 1 is actually implementing a fully connected layer. It takes 4096 input values. It emits 4096 output values based on a matrix of weights 4096 by not 4096 in size, plus the bias. So anyways, deep neural networks looks a bit like this from a high level. There's a bunch of in the input layers. There's a bunch of ports for a data element, for example, a floating value. Each floating value coming into an input layer element, input layer node per instance, per cycle, so to speak. And there's also a bunch of output layer nodes, which can emit one output per input. And of course, initially, when we thought of long time ago, when we thought of neural networks, we typically thought of single layer neural networks. But now we know that we do need deep neural networks with more than one hidden layers to actually get useful computation. And each of these output nodes represent a classification class. So each of these nodes will emit a floating point value for whether this node thinks, so each, at least at the output level, each of these nodes represent a class. So this node will represent a goldfish class, this node will represent the Palace class, so on and so on and so on. And each node for each input data, output node for each input data will emit a value thinking, oh, I think I'm a goldfish node. I think this input photo has a certain percent chance that this is a goldfish. Yeah, and lab 1 has been dealing with pretty much one of these layers, one of these intermediate layers. And we'll do pretty much the same thing for lab 2 as well. And the interesting part of neural networks is the internals of this one artificial neuron. So each of these yellow circles, the intermediate layers, the hidden layers, each of these circles represent a artificial neuron, which looks a bit like this. And what each of these neurons do mathematically is fairly simple. You've already seen this in lab 1. All it does is that it takes as input, so each of these nodes takes as input the output of every single node in the previous layer. So, and let's say because there are, let's compare this to lab 1. Because we have 4,096 outputs that we want to create from each of these, from 4,096 output. And we take as input from another set of 4,096 nodes from the previous layer, meaning there are 4,000, because each of these nodes have 4,096 connections talking to every single node in the previous layer. Each node has 4,096 edges going to the previous layer. And because we have 4,096 nodes in this current layer, it represents 4,096 by 4,096 weights, one for each edge. That's where the 4,096 by 4,096 size comes from. And the computation that each of these nodes do is very simple. For each edge, let's say this node is connected to this node over an edge. For each edge, it multiplies the weight of the edge by the output of the previous node. So the output of this node. It multiplies it, adds it to, and also does the same for this node, for this node, for this node, and for this node, and for this node, and adds all of it together. So there's a lot of input coming in on this side. It says input here. A lot of input coming in from each of the previous nodes. It multiplies it against each of the weights that are assigned to the edge. Also, there's the bias, and then adds everything together. That's pretty much what we've been doing. And then it goes through a so-called activation function. So the sum, the singular value coming out of this one node goes through a so-called activation function. Depends on your model design. It can be using one from a various set of activation functions. For example, you can be using a sigmoid that looks like this, trigonometric function, or you can be using something like a rectified linear unit, which is what we use for lab 1, which is what is actually used for that particular layer in the VGG19 model, where when the input is larger than 0, it just emits the same value. If the input is smaller than 0, then it just emits 0. Right. So effectively, what each of these neurons do is effectively just multiplying a weight vector by the input vector. So if there's 4,096 neurons in the previous layer, we're pretty much just multiplying the input vector of length to 4,096 by the weight vector of size 4,096 to obtain a single scalar value, and then push it through an activation function, which adds non-linearity to the model. So this is pretty computationally simple. I mean, conceptually simple. Computationally, it does a lot of work. So that's the fully connected layer, which we have dealt with in lab 1, which we'll again deal with in lab 2. Then we move on to the convolution layer. the convolution layer performs the convolution on the input matrix and emits a new output matrix. And what it does is, again, conceptually very simple. Every single convolution works with a convolution filter, a convolution matrix, which is smaller in size compared to the actual input. In many cases, the filter size is typically something like 3 by 3 or 5 by 5, sometimes even 1 by 1 or something like that. And what it does is that it moves this filter, and we'll show an example of this in the next slide. We slide this filter across every single location in the input matrix, performs the convolution, and we'll show what that exactly is if you're not familiar with it in the next slide as well. And for each filter application, so this 3 by 3 filter being applied to this particular location results in a value being updated for this one location. And then we move this forward, slide it over every single possible location to fill out the entirety of the output matrix. And once we have a very large output matrix, some layers have what is called the pooling layer, so which makes the size of the matrix smaller. So if you have a 2 by 2 pooling layer, we will group units of 2 by 2 submatrices, and sometimes we can do averages or maxes or mins or whatever to turn it into a smaller size matrix for the next layer, to reduce the work in the next layer, for example. So this is what convolution layers typically consist of. If you actually look at an example of a convolution, many, not just for neural networks, a lot of operations, a lot of computation can be expressed in terms of convolutions. A lot of linear algebraic problems can be expressed in terms of convolutions. Things like edge detection, image blurring, these things can be expressed in terms of convolutions. So it's a very generic way of doing computation on a matrix of values. Anyways, so say we want to apply this convolution filter to this input map to obtain an output map. So the computation that would be actually done is multiply the values in the same sublocations pretty much. 1 multiplied by 0, 2 multiplied by 1, 3 multiplied by 0, -2 multiplied by 2, 0 multiplied by 4, so on and so on and so on, and then add everything together, which results in a value of 44, and you write the value to the output map. Depends on your implementation. You can, because if you slide it forward like this, because we won't be emitting values for this 0, this cornermost cell, for example, you can either create an output map that is smaller than the input map, or you can pad the edges with zeros to create the same size output map as the input map. It depends on your model design. Yeah, but typically you can add 0 padding to source matrix to maintain the dimensions, to have the same size output map as the input map. It depends on your model. And we can keep going forward. For example, we can add we can slide the filter 1 position forward. Now we're looking at this sublocation, and then we can do the same. 1 multiplied by 1. Oops. Hey, this equation didn't change, but it's straightforward enough. 1 multiplied by 1, 0 multiplied by 2, 1 multiplied by 3, so on and so on, to get the next position in the output map. And we keep doing this until we have slid through the entire input map. And in neural networks, we typically use multi-dimensional convolution, partially because the so-called feature map, the input, has multiple layers, multiple dimensions as well. For example, if you have an image as an input, an image has R, G, and B layers representing 3 different dimensions of values through RGB layers or RGB channels. So there's 3 channels of an input map. And one layer, one convolutional layer can have, before we get there, if we have a 3-dimensional input map, 3-channel input map, we can also have convolution filters that are also 3-dimensional. For example, instead of the simple example we saw before is a simple 3 by 3 2-dimensional filter, but some models can actually use three-dimensional filters, 3x3x3 filters, which looks at 3x3 filters in all input channels at the same position. And this one filter will emit a single two-dimensional feature map, because this 3x3x3 filter being applied to a single location results in a single scalar value. And this whole thing is sliding through the XY dimensions of the input feature map. So this convolution results in a single two-dimensional output feature map. But because one layer can also have many convolution filters, many of these things, the output map can also become multiple channels. So yeah, it can take multiple channels as input, emit multiple channels as output. So that's what the convolution layer does. Yeah, this just to show visually, we can have multiple filters, multiple multidimensional filters looking through a single multidimensional feature map, and emit each of these filters will output different channels, and the input to the next layer, for example, would be a 4x4x2, because there's two of these things, input map. So you can imagine a lot of the work that's being done is multiply accumulates, pretty much just multiplying the weights to a value and then adding everything together. So it shares a lot of characteristics with the matrix multiplication stuff again. And just for fun, this is an example of the learned convolution filters for an image recognition neural network model. You can see, let's see what's this one. Yeah. And there are multiple, you can see, I forgot exactly how many, but you can see that there's many convolution filters that are being trained. And roughly, just looking at it from a intuitive level, we can see some of these kernels some of these filters have been trained to recognize a slanted edge, more slanted edge, a horizontal edge, so on and so on, sometimes color relations and things like that. So, for example, this lowest level convolution layer has, after training, has learned to recognize lower level features in the image. And I would guess that as we move forward into the upper levels in the neural network, it would have been trained to recognize higher level features like edges or corners, or at later points in time, faces and things like that. And there are other machine learning methods that are not deep neural networks, which take this kind of approaches as well, especially these kind of filters, these black and white edge detecting filters look very similar to a face detection method, or not just for face detection, but image detection of objects in the image method called Haar cascades. But in those kinds of approaches, these weights are handcrafted by people, scientists, as opposed to being automatically trained by models. And these have been shown to work better, I guess. Yeah. And as we move forward in the convolution layers, we can apply all of these convolution filters to an input image, which will emit different output feature map, which will have which are each results of sliding these filters onto the input image. And this output feature map will be fed to the next layer. The next layer could be another convolution layer. It could be a fully connected layer. And the computation that is actually being done, at least in the convolution layer, is again very conceptually simple, although it represents, the simple conceptual computation represents a lot of computation, but conceptually it's simple. It looks like this. So if you delve through the actual cascade of for loops, we are looping through the images, the input images. We are looking through the actual filters. We want to apply to each input image. We can have 64 filters, convolution filters applied to each image, for example. For each filter consists of a two-dimensional filter, multiple two-dimensional filters, and it has, if the input image has NC, in this example, C input channels, we have to apply C number of two-dimensional filters to each input channel. For each input channel application, we loop through the rows of the input image, one channel of the input image, the columns of the input image. So we're looping through the entire thing, the entire channel. And for each location in the image, we're also looping through the locations in the filter row, and then the filter column, because we have to use each of the locations in the filter, all of the weights of the filter to determine a single position in the output. And then for each of these, putting all of these for loops together, what we're basically doing is in the output feature map, we are doing multiply accumulation. We're just doing a lot of it. And again, you can see something like a fuse multiply add, or pretty much floating point multiplication and floating point addition is the key work that is being done for the convolution layer. Just like, and this is pretty much the same at a high level to the fully connected layer example that we were looking at, which is pretty much just doing matrix-matrix multiplication, which almost completely consists of floating point multiplication and then floating point addition. So you can kind of see a theme here. This is just here for completeness. We talked about the pooling layer already. It reduces the size of the feature map. You can either do things like max pooling, where it takes the maximum value from the window. So in this set of four green blocks, 65 is the largest. So we take 65, so on and so on, to reduce the size of the feature map, to reduce the size of the input that goes into the next layer, to reduce the computational overhead if this doesn't cause reduction in accuracy. And yeah. An example of a real convolutional neural network is the AlexNet model, which is arguably the model that started this whole thing. And it'll be interesting to see, I kind of alluded to this already. We have a 3-channel, because RGB, fixed size images of 224 by 224 being fed into the neural network. And there's a bunch of convolution layers, and then a bunch of fully connected layers. But interestingly, there's two different pipelines of convolution layers and two different pipelines of fully connected layers. I mentioned this, the reason for this already, because the GPUs they were using at the time did not have enough memory on board to keep the entire set of this whole neural network in memory during training. So they had to use 2 GPUs. So the weights had to be distributed across 2 GPUs. And the model has to be designed such that the communication there's not too much communication between these GPUs. If there's too much communication between the 2 GPUs, that would have, the communication bottleneck would have just completely killed performance. So that's why the model looked like this. It was kind of funny seeing back in 2012-ish, when this thing first came out, and we had much less knowledge about what made AlexNet as good as it did at the time. And people didn't know too much about which of these design decisions had what kind of impact on the accuracy and performance of the neural network. We still don't know too much, but at the time we knew very little. So there was a lot of research papers, a lot of research neural networks being constructed at the time, which had their pipelines divided into twos like this, even if they actually had computing power capable of just having one pipeline, because they didn't know at the time, this division of 2 pipelines, was it actually giving beneficial, having beneficial impact on the accuracy? So they were kind of afraid to touch that. But now we know better. So yeah, each of these convolution layers have consists of, for example, this particular one has 128 filters, and so on and so on. Yeah, a simplified intuition is that higher order information exists at the later layers. In the earlier layers, it detects edges and things like that. In the later layers, it detects faces and arms and ears and edges and drawers and wheels and things like that. And at the dense layers, all of that information is being stitched together to determine what exactly this object is. There are papers that actually argue that this is not necessarily what's happening. Even higher level information hints still exists at the lower layers, and the lower level informations are still being determined at the higher layers. So it's not a very clear-cut distinction, but it's a simplified intuition to have. Another example is the VGG16 model, where you notice that this time it's just a single pipeline. This was it was one of the winners at the image recognition challenge in one of the years. I forgot which. But it has a single pipeline. But the structure conceptually is pretty much the same. It has a bunch of convolution layers with max pooling layers here and there, the red blocks. The black blocks are the convolution layers with rectified linear activation functions. And after we get to the end, we have a bunch of fully connected layers. And at the very last fully connected layer, it emits a vector of 1,000 floating point values. And we run softmax on it, meaning we discover which of these slots which of the 1,000 slots have the highest probability, which tells us which image are we looking at. To kind of put things into scale, the size of the VGG16 model contains 138 million weights. 138 million weights, meaning if each weight is 4 bytes, single precision floating point integer, the weight size is something like 400, 500 megabytes, which is not small. It's not huge, but it's not small either. And during the process of performing inference on a single 224 by 224 input image, it needs to perform 15.5 giga multiply accumulation. So about 30 giga floating point operations. So if you remember the lab 1 work that you've done, and say you have reached 30 gigaflops over 4 cores, 30 gigaflops, so 30 giga floating point operations per second. This inference of this single model, this one model on a single image, requires 30 gigaflops. So if you had a model like that, if you had a model like this, which is by today's standards pretty simple model, and if you had built a fairly optimized software implementation like the ones you built for Lab 1, you can be running maybe inference at 1 image per second on 4 threads. Of course, some of you have come up with better implementations. With that, you can do 3, 4 image recognitions per second. But imagine if you want to put this on a self-driving car and you want to run a model that's much, much more complex than this, like YOLOnet or whatever, ResNet, something. And if your car is doing image recognition or object detection at 5 frames per second, that would be a very dangerous car to be self-driving. So that's not very good. That's not what we want. So this is kind of the scale in the number of weights and the size, the amount of computation that we have to do to run this kind of neural network model. So this is the systems aspect of neural networks. So yeah, if we are running a fairly powerful machine at full 100% load, maybe we can do 2, 3, 4 image recognitions per second. So this does represent quite a bit of computational overhead. So this was VGG16 back in 2016 or so. We have now seen much, much more complex models. GoogleNet, ImageNet 2014 winner, kind of breaks away from the uniform convolution layers and deep fully connected layers model. Each of these blocks represent sub neural networks, which each of these have fully connected and convolution layers. And the example here is ResNet below. This is from, I think, from Microsoft. It is an ImageNet 2015 winner. And you can see that there are layers that jump forward and things like that. So each of these models, YOLOnet is a model for object detection. So if you give it an image, it draws rectangles around the images that it detects. And each of these models do share common building blocks. meaning they do still use things like convolution, they still use things like fully connected layers and things like that, max pooling. But these, you can see that these look kind of drastically different. And the accuracy of these models for various applications are pretty impressive. I've recently read a paper which we're using ResNet, and I'm kind of curious what their rationale for using ResNet in particular was, because for the job at hand, it looked like a pretty overkill kind of a model. But there was a paper that was using a ResNet neural network structure trained to recognize ECG data, so heartbeat data, the electrocardiogram data. And the neural network model was able to recognize a potential near future heart attack at a better accuracy than trained human physicians and things like that. So there's a lot of applications for these things, but we won't go, at least for the purpose of this lecture, we won't go into too much details about these new and different neural network models, because we want to start focusing on the systems and computation aspects of this. And yeah, and before we actually get on started, there's a beware and disclaimer on these accelerators. This field is advancing very quickly and it's kind of messy right now. Oops, messy right now. Although things have seemed to be kind of quieting down in the past couple of years, but a couple of years ago, there were thousands of new papers improving upon everyone else, coming out every week, it looked like. Things are kind of settling down recently, it seems, but anyways. There's lots of papers and implementations always beating each other with seemingly contradicting results. So yeah, it's important to keep our eyes wide open when we're trying to parse these kind of resulting data. But at least for the purpose of this lecture, we're going to focus on some of the more established applications, for example, image recognition, and some of the more easier to understand models like the deep convolutional neural networks. Yes. With that disclaimer, I guess we may have time to get a little bit into the actual meat of the content. Yeah, going into the needs for having neural network accelerator. From a couple of slides ago, remember that 3GZ16 requires 138 million weights and 15.5 gigamax multiply accumulators to process one input image. And this numbers became less important now that we actually tried doing this with Lab 1. But say if we have a CPU running at 3 gigahertz, one IPC, 3 giga operations per second, that will require 5+ seconds per image per thread. But since we, for the purpose of Lab 1, we've already improved upon this using AVX and multi-threading, so we know what the actual numbers were going to look like. Also, CPUs do constitute significant power consumption. If we optimistically assume 3 gigaops per thread, but now we know that the actual numbers that we can get is much larger than this. 8 threads running at 100 watts. That's not a very large number of gigawatts per watt, gigaops per watt. The actual number is slightly larger than this with AVX and whatnot, but you get the picture. So here's a sorry. Here's a kind of an old data from back from 2011, but this was a good comparison that I could find. If you compare the gigaops performance, power consumption, and the resulting gigaops per watt for CPUs, GPUs, mobile GPUs, FPGAs, and ASICs, first of all, the actual performance increases by leaps and bounds as we move forward into different implementation architectures. The Core 2 Duo, so it's a very old processor, gigaops 1. We know that we can do much better than this on our modern processors now. But let's, for the sake of comparison, see the desktop CPU was getting about 1 gigaops. Compared to that, even this much of a time ago, if you look at the performance of a mobile GPU and an actual GPU, a desktop class GPU, GTX 480, that's an old GPU by today's standards. If you compare it to gigaflops, this is still giving us much better performance than what we are getting with as a result of Lab 1. At least I don't think any of us are getting almost 300 gigaflops on our desktop machines. And similar with FPGAs, this is, what is this? Vertex 6 is a not a very old, but it's a relatively old FPGA. Gets you this much performance. If you actually synthesize it into ASICs and you actually get even here, 45 nanometers by today's standards is very old technology. If you were to do this now, if you were to start a startup doing something like this today, you would absolutely aim for either 10 or 7 nanometer fabrication process. But even then, the gigaflops, we were getting over a teraflop of performance. It becomes more valuable. These numbers become more valuable if you actually look at the power consumption. 30 watts for the Core 2 Duo. We know that for the modern processors like i7s that we're running these things on, they do consume more than 30 most of the time. GPUs, this fast GPU is consuming 200, mobile GPU consuming 30, the FPGA consuming 10, and the ASIC consuming just 5 watts. And if we actually normalize for the power consumption to get the power efficiency, there is orders of magnitude benefits compared to CPUs, 0.04 gigaops per watt, to GPUs, slightly more than 1 gigaops per watt. So this is almost 2 orders of magnitude better. FPGAs get almost 3 orders of magnitude better. And an ASIC gives you 4 orders of magnitude better. So given that in modern data centers, power consumption is a pretty significant factor in the whole overall cost of operating your data center. And we'll actually talk about this in one of the later lectures, breaking down the power consumption of data centers. It's actually a fascinating topic. And if you want to put this on cars, if you want to put this on smart speakers, if you want to put this on laptops and phones, power consumption and power efficiency becomes a pretty dominant factor in the system design. There was actually recent, and I say recent about 2-3 years ago, there was actually a paper on the power consumption overhead of computation on self-driving cars. And I think in that example, they were using electrical cars because the power consumption numbers were fairly large that just, having just piggybacking off car batteries wasn't going to cut it. So if they drained the main battery of electrical cars like Teslas for the purpose of self-driving car computation, the computation fabric that you use, if you use CPUs, if you use GPUs, if you use ASICs, if you use FPGAs, the choice of computation fabric was actually having tangible impact on the maximum distance that your car can travel by tens of %. So this is a pretty close to the skin kind of a noticeable impact on system design, why it's important.